All right, hello everybody. Welcome back into the channel. Hope you're having a wonderful day so far. My name is Michael. Today we're going to be jumping back into C Programming: A Modern Approach, second edition by K.N. King. We're going to be starting and reading chapter 9 today, Functions. So hope you're having a wonderful day and welcome in. This is the condensed version from the live stream. If you want to join us live as we read through the entire chapter and take notes in a more robust and interactive fashion, please do so. Other than that, you can enjoy the condensed read-aloud audiobook version here. The notes that you see at the right side of my screen can be found within a GitHub repo linked down in the description. Thanks so much for being here, and let's go ahead and get started. Chapter 9, Functions. If you have a procedure with 10 parameters, you probably missed some. We saw in Chapter 2 that a function is simply a series of statements that have been grouped together and given a name. Although the term function comes from mathematics, C functions don't always resemble math functions. In C, a function doesn't necessarily have arguments, nor does it necessarily compute a value. In some programming languages, a function returns a value, whereas a procedure doesn't. C lacks this distinction. Functions are the building blocks of C programs. Each function is essentially a small program with its own declarations and statements. Using functions, we can divide a program into small pieces that are easier for us and others to understand and modify. Functions can take some of the tedium out of programming by allowing us to avoid duplicating code that's used more than once. Moreover, functions are reusable. We can take a function that was originally part of one program and use it in others. Our programs so far have consisted of just the main function. In this chapter, we'll see how to write functions other than main, and we'll learn more about main itself. Chapter 9.1 shows how to define and call functions. Section 9.2 then discusses function declarations and how they differ from function definitions. Next, Section 9.3 examines how arguments are passed to functions. The remainder of the chapter covers the return statement. Section 9.4, the related issue of program termination, Section 9.5, and recursion in Section 9.6. 9.1, defining and calling functions. Before we go over the formal rules for defining a function, let's look at 3 simple programs that define functions. Computing averages. Suppose we often need to compute the averages of the 2 double values. The C library doesn't have a, quote, average function, but we can easily define our own. Here's what it would look like. Double average takes in a double A and double B. Return A plus B divided by 2. The word double at the beginning is average's return type, the type of data that the function returns each time it's called. The identifiers A and B, the function's parameters, represent the 2 numbers that will be supplied whenever average is called. Each parameter must have a type, just like every variable has a type. In this example, both A and B have type double. It may look odd, but the word double must appear twice, once before A and once before B. A function parameter is essentially a variable whose initial value will be supplied later, when the function is called. Every function has an executable part called the body, which is enclosed in the braces. The body of average consists of a single return statement. Executing this statement causes the function to return to the place from which it was called. The value of A plus B over 2 will be the value returned by the function. To call a function, we write the function name, followed by a list of arguments. For example, average xy is a call of the average function. Arguments are used to supply information to a function. In this case, average needs to know which 2 numbers to average. The effect of the call average xy is to copy the values of x and y into the parameters a and b, and then execute the body of average. An argument doesn't have to be a variable. Any expression of a compatible type will do, allowing us to write average 5.1, 8.9, or average x over 2, y over 3. We'll put the call of average in the place where we need to use the return value. For example, we could write printf average is %g \n, call to average xy, to compute the average of xy and then print it. This statement has the following effect. The average function is called with x and y as arguments. X and Y are copied into A and B parameters. Average executes its return statement, returning the average of A and B. Printf prints the value of average, returns. The return value of average becomes one of printf's arguments. Note that the return value of average isn't saved anywhere. The program prints it and then discards it. If we need the return value later in the program, we could have captured it in a variable, such as average equals to average of x, y. This statement calls average, then saves its return value in the variable avg. Now, let's use the average function in a complete program. The following program uses 3 numbers and computes their averages one pair at a time. Enter 3 numbers: 3.5, 9.6, 10.2. Average of 3.5 and 9.6, 6.5. Average of 9.6 and 10.2, 9.9. Average of 3.5 and 10.2 is 6.85. Among other things, this program shows that a function can be called as often as we need. Average.c computes a pairwise average of 3 numbers. Include standard io.h. We define a double average, double A, and double B parameters, which returns the average, which is A plus B over 2. We then have a main function, which takes in 3 double values, x, y, and z. We call printf to enter these numbers and scan them into the values of x, y, and z. We then compute the average using the call to average for the pairwise averages of x, y, and z, and return 0. Notice that I put the definition of average before main. We'll see in section 9.2 that putting average after main causes problems. Program printing a countdown. Not every function returns a value. For example, a function whose job is to produce output may not need to return anything. To indicate that a function has no return value, we specify that its return type is void. Void is a type with no values. Consider the following function, which prints the message t minus n and counting, where n is supplied when the function is called. Void print count int n. Printf t minus %d and counting, and put in the value of n. Print count has one parameter, n, of type int. It returns nothing, so I've specified void as the return type and omitted the return statement. Since print count doesn't return a value, we can't call it in the same way we call average. Instead, a call of print count must appear in a statement by itself, such as print count of I, semicolon. Here's a program that calls print count 10 times inside of a loop. Countdown.c prints a countdown. We include standard IO. We have a void return of print count function, which takes in an integer. We then print this statement, inserting the integer into the print statement. We then, in the main function, have int I. For I equals to 10 up until I is 1 inclusive, we're going to print the value of I and reduce it each time, 10, 9, all the way to 1. Initially, I has the value of 10. When print count is called for the first time, I is copied into n, so that n takes on the value 10 as well. As a result, the first call of print count will print t minus 10 and counting. Print count then returns to the point at which it was called, which happens to be the body of a for statement. The for statement resumes where it left off, decrementing I to 9 and testing whether it's greater than 0. It is, so print count is called again, and this time printing t minus 9 and counting. Each time print count is called, I is different, so print count will print 10 different messages. Printing a pun revisited. Some functions have no parameters at all. Consider print pun, which prints a bad pun each time it's called. Void print pun void. So this function has no parameters and no return type. Printf to see or not to see, that is the question. So it's just a single print statement. The word void in the parentheses indicates that print pun has no arguments. This time we're using void as a placeholder. That means nothing goes here. To call a function with no arguments, we write the function's name followed by parentheses, print pun, parentheses, parentheses, semicolon. The parentheses must be present even though there are no arguments. Here's a tiny program that tests the print pun function. Pun2.c print a bad pun. Include the standard IO, void print pun void. We print that pun within this print pun function. In the main function, we call the print pun and then return 0. The execution of this program begins with the first statement in main, which happens to be a call of print pun. When print pun begins to execute, it in turn calls printf to display a string. When printf returns, print pun returns to main. Function definitions. Now that we've seen several examples, let's look at the general form of a function definition. Return type, function name, parentheses, parameters, parentheses, curly brace, declarations, statements, curly brace. The return type of a function is the type of value that the function returns. The following rules govern the return type. Functions may not return arrays, but there are no other restrictions on the return type. Specifying that the return type is void indicates that the function doesn't return a value. If the return type is omitted in C89, the function is presumed to return a value of type int. In C99, it's illegal to omit the return type of a function. As a matter of style, some programmers put the return type above the function name. Double average. Interesting. Putting the return type on a separate line is especially useful if the return type is lengthy, like unsigned long int. After the function name comes a list of parameters. Each parameter is preceded by a specification of its type. Parameters are separated by commas. If the function has no parameters, the word void should appear between the parentheses. Note, a separate type must be specified for each parameter, even when several parameters have the same type. Double average, double a comma b is wrong. The body of a function may include both declarations and statements. For example, the average function could be written as so: double average, double a comma double b. We have a declaration of double sum, where we cause sum to be the sum of a plus b, and then divide the value of sum by 2 and return that value, having a declaration and 2 statements. Variables declared in the body of a function belong exclusively to that function. They can't be examined or modified by the other functions. In C89, variable declarations must come first before all statements in the body of a function. In C99, variable declarations and statements can be mixed as long as each variable is declared prior to the first statement that uses the variable. Some pre-C99 compilers also allow mixing of declarations and statements. The body of a function whose return type is void, which I'll call a, quote, void function, can be empty. Leaving the body empty may make sense during program development. We can leave room for the function without taking the time to complete it, then come back later and write the body. Function calls. A function call consists of a function name followed by a list of arguments enclosed by parentheses. Average, x, y, print count, I, print pun. If the parentheses are missing, the function won't get called, such as print pun semicolon, which is wrong. The result is a legal, albeit meaningless expression statement that looks correct, but has no effect. Some compilers issue a warning such as a, quote, statement with no effect, close quote. A call of a void function is always followed by a semicolon to turn it into a statement. Print count takes in I as a parameter, semicolon. Print pun takes in nothing as the parameters, semicolon. A call of a non-void function, on the other hand, produces a value that can be stored in a variable, tested, printed, or used in some other way. We can average equals to average of x, y. If this computed value is greater than 0, then print the average is positive, and then we can say the average is this. The value returned by a non-void function can always be discarded if it's not needed. Average x, y discards the return value as we're not saving it in a variable. This call of average is an example of an expression statement, a statement that evaluates an expression but then discards the result. Ignoring the return value of average is an odd thing to do, but for some functions it makes sense. The printf function, for example, returns the number of characters that it prints. After the following call, numchars will have the value 9. Numchars equals to printf, quote, hi, comma, mom, exclamation mark, backslash, n, close quote. Since we're probably not interested in the number of characters printed, we'll normally discard printf's return value by just calling printf by itself with no variable saving. To make it clear that we're deliberately discarding the return value of a function, C allows us to put void before the call, parenthesis void, parenthesis printf. What we're doing is converting the return value of printf to type void. In C, quote, casting to void, close quote, is a polite way of saying, quote, throwing away, close quote. Using parenthesis void, parenthesis, or casting void makes it clear to others that you deliberately discard the return value, not just forgot that there was one. Unfortunately, there are a great many functions in the C library whose values are routinely ignored. Using parenthesis void, parenthesis, when calling all them can get tiresome, so I haven't done so in this book. Program, testing whether a number is prime. To see how functions can make programs easier to understand, let's write a program that tests whether a number is prime. The program will prompt the user to enter a number, then respond with a message indicating whether or not the number is prime. Enter number 34, not prime. Instead of putting the prime testing details in main, we'll define a separate function that returns true if its parameter is a prime number and false if it isn't. When given a number, n, the isPrime function will divide n by each of the numbers between 2 and the square root of n. If the remainder is ever 0, we know that n isn't prime. Test whether a number is prime. Include standard bool and include standard IO. We define a isPrime function which returns a boolean and takes in an integer. We have a declared int divisor. If the n provided is less than or equal to 1, we return false. For divisor is equal to 2 and divisor times divisor is less than or equal to n, we're going to continually increase the divisor value. If the remainder of n divided by the divisor is 0, we're going to return false, else we're going to return true at the end of the loop. Int main void. Int n, printf, enter a number. Scanf, we're going to read that number into n. If is prime on n, printf prime, else printf not prime, return 0. Notice that main contains a variable named n, even though isPrime's parameters is also named n. In general, a function may declare a variable with the same name as a variable in another function. The two variables represent different locations in memory, so assigning a new value to one variable doesn't change the other. This property extends to parameters as well. Section 10.1 discusses this point in more detail. As isPrime demonstrates, a function may have more than one return statement. However, we can execute just one of these statements during a given call of the function, because reaching a return statement causes the function to return to where it was called. We'll learn more about the return statement in section 9.4. 9.2 Function declarations. In the programs in section 9.1, the definitions of each function was always placed above the point at which it was called. In fact, C doesn't require that the definitions of a function precede its calls. Suppose that we rearrange the average.c program by putting the definition of average after the definition of main. Include the standard IO into main void with the function there. And then after the main function, we have the double average function. When the compiler computes the first call of average in main, it has no information about average. It doesn't know how many parameters average has, what the types of these parameters are, or what kind of values average returns. Instead of producing an error message, though, the compiler assumes that average returns an int value. Recall from section 9.1 that the return type of a function is int by default. We say that the compiler has created an implicit declaration of the function. The compiler is unable to check that we're passing average the right number of arguments and that the arguments have the proper type. Instead, it performs the default argument promotions and hopes for the best. When it encounters the definition of average later in the program, the compiler notices that the function's return type is actually double, not int, and so we get an error message. One way to avoid this problem of call before definition is to arrange the program so that the definition of each function precedes all its calls. Unfortunately, Such an arrangement doesn't always exist, and even when it does, it may make the program harder to understand by putting its function definitions in an unnatural order. Fortunately, C offers a better solution. Declare each function before calling it. A function declaration provides the compiler with a brief glimpse at a function whose full definition will appear later. A function declaration resembles the first line of a function definition with a semicolon added at the end. Needless to say, the declaration of a function must be consistent with the function's definition. Here's how our program would look with a declaration of average added. We include standard I/O. We have a declaration before the main function of double average, which has parameters of double A and double B. We then have our main function, and then we have our average function below. Function declarations of the kind we've been discussing are known as function prototypes. To distinguish them from an older style of function declaration in which the parentheses are left empty, a prototype provides a complete description of how to call a function, how many arguments to supply, what their type should be, and what type of result will be returned. Incidentally, a function prototype doesn't have to specify the names of the function parameters as long as their types are present. Double, average, double, double. It's usually best not to omit parameter names since they help document the purpose of each parameter and remind the programmer of the order in which arguments must appear when the function is called. However, there are legitimate reasons for omitting parameter names and some programmers prefer to do so. C99 has adopted the rule that either a declaration or definition of a function must be present prior to any call of a function. Calling a function for which the compiler has not yet seen a declaration or definition is an error. Chapter 9, 9.3, Arguments. Let's review the difference between a parameter and an argument. Parameters appear in function definitions. They're dummy names that represent values to be supplied when the function is called. Arguments are expressions that appear in the function calls. When the distinction between arguments and parameters isn't important, I'll sometimes use argument to mean either. In C, arguments are passed by value. When a function is called, each argument is evaluated and its value is assigned to the corresponding parameter. Since the parameter contains a copy of the argument's value, any changes made to the parameter during the execution of the function don't affect the argument. In effect, each parameter behaves like a variable that's been initialized to the value of the matching argument. The fact that arguments are passed by value has both advantages and disadvantages. Since a parameter can be modified without affecting the corresponding argument, we can use parameters as variables within the function, thereby reducing the number of genuine variables needed. Consider the following function which raises a number x to power n. Int power, which takes in int x and int n. We declare int I and int result, which equals to 1. For I equals to 1, while I is less than or equal to n, I plus plus, result equals to result times n. Return result. Since n is a copy of the original exponent, we can modify its inside the function, thus removing the need for I. Int power, int x, int n, int result equals to 1, while n less than is greater than 0, result equals to result times n. Unfortunately, C's requirement that arguments be passed by value makes it difficult to write certain kinds of functions. For example, suppose that we need a function that will decompose a double value into an integer part and a fractional part. Since a function can't return two numbers, we might try passing a pair of variables to the function and having it modify them. Void decompose, which takes in double x, long int part, and double frac part. Int underscore part equals to long cast of the x variable, which drops the fractional part. Frac part equals to x minus the integer part, which just leaves the decimal portion. Suppose that we call the function in the following way. Decompose pi, which is 3.14159, I, and d. At the beginning of the call, 3.14159 is copied into x, which is a double. I's value is copied into int part, and d's value is copied into frac part. The statement inside decompose, then assign 3 to int part and 0.14159 to frac part, and the function returns. Unfortunately, I and D weren't affected by the assignments to int part and frac part, so they have the same values after the call as they did before the call. With a little extra effort, decompose can be made to work, as we'll see in section 11.4. However, we'll need to cover more of C's features first. Argument conversions. C allows function calls in which the types of the arguments do not match the types of the parameters. The rules governing for how the arguments are converted depend on whether or not the compiler has seen a prototype for the function or the function's full definition prior to the call. The compiler has encountered a prototype prior to the call. The value of each argument is implicitly converted to the type of the corresponding parameter as if by assignment. For example, if an int argument is passed to a function that was expecting a double, the argument is converted to a double automatically. The compiler has not encountered a prototype prior to the call. The compiler performs the default argument promotions. 1. Float arguments are converted to double. 2. The integral promotions are performed, causing char and short arguments to be converted to int. In C99, the integer promotions are performed. Relying on the default argument promotions is dangerous. Consider the following program. Include standard.io.h, int main void. We declare a x variable, which is a double and has a value of 3.0. We printf square and insert the value of a function call square of x. So square, right, which is here, returns an int and takes in an int and returns that int times the int. At the time square is called, the compiler hasn't seen a prototype yet. There's no prototype above the main function before it's called, right? So it doesn't know that the square expects an argument of type int. Instead, the compiler performs the default argument promotions on x with no effect. Since it's expecting an argument of type int, but has been given a double value instead, the effect of calling square is undefined. The problem can be fixed by casting square's argument to the proper type. Printf, quote, square, %d \n, square, cast int onto x. Of course, a much better solution is to provide a prototype for the square before calling it. In C99, calling square without first providing a declaration or definition of the function is an error. Array arguments. Arrays are often used as arguments when a function parameter is a one-dimensional array. The length of the array can be, and normally is, left unspecified. Int f, which takes in an int array a, no length specified. The argument can be any one-dimensional array whose elements are of the proper type. There's just one problem. How will f know how long the array is? Unfortunately, C doesn't provide any easy way for a function to determine the length of an array passed to it. Instead, we'll have to supply the length, if the function needs it, as an additional argument. Although we can use the size of argument to help determine the length of an array variable, it doesn't give the correct answer for an array parameter. Int f takes in an array of type int. We say that the int length is equal to the size of a over the size of a index of 0. This is wrong, not the number of elements in a. Section 12.3 explains why. The following function illustrates the use of one-dimensional array arguments. When given an array of a of int values, sum array returns the sum of elements in the array a. Since sum array needs to know the length of a, we must supply it as a second argument. Int sum underscore array takes in an integer array a and a single integer value. We define a sum equals to 0 and declare an int I variable. Both of these are ints. For I equals to 0, while I is less than n, increase I, sum will increase by the value of the array at index of I, and return the sum at the very end. The prototype for sum array has the following appearance: int sum array, int a array, and int n. As usual, we can omit the parameter names if we wish. When sum array is called, the first argument will be the name of an array, and the second argument will be its length. For example, define len 100. We have a main function, and we call a variable b, which is an array of size length 100, and an integer total. We say total is equal to sum array given the array b and the length of len. Notice that we don't put brackets after an array name when passing it to a function. This is wrong. An important point about array arguments: a function has no way to check that we've passed it the correct array length. We can exploit this fact by telling the function that the array is smaller than it really is. Suppose that we've only stored 50 numbers in the b array, even though it could hold 100. We can sum just the first 50 elements by writing the 50 directly in for that parameter, with 50 as that argument, right? Sum array will ignore the 50 other elements. Indeed, it won't know that they even exist. Be careful not to tell a function that an array argument is larger than it really is, such as 150 in for that argument. In this example, sum array will go past the end of the array, causing undefined behavior. Another important thing to know is that a function is allowed to change the elements of an array parameter, and the change is reflected in the corresponding argument. For example, the following function modifies an array by storing 0 into each of its elements. Void stores zeros, takes in an array of integers and an integer n. We declare an int I for I equals to 0, while I is less than n, I++. We assign all the values in the array at index of I equal to 0. The call store underscore 0 of b 100 will store zeros into the first 100 elements of the array b. This ability to modify the elements of an array argument may seem to contradict the fact that C passes arguments by value. In fact, there's no contradiction, but I won't be able to explain why until section 12.3. If a parameter is a multidimensional array, only the length of the first dimension may be omitted when the parameter is declared. For example, if we revise the sum array function so that A is a two-dimensional array, we must specify the number of columns in A, although we don't have to indicate the number of rows. So we define len to be 10. We have int sum two-dimensional array, which takes in an integer array A of addition of row columns length, and int n. Right, for I equals 0, I is less than n, I++. For j equals to 0, j less than length, the columns, j++. Sum plus equals to a index I index j, return sum. Not being able to pass multi-dimensional arrays with an attribute number of columns can be a nuisance. Fortunately, we can often work around this difficulty by using arrays of pointers. C99's variable length array parameters provide an even better solution to the problem. C99 variable length array parameters. C99 adds several new twists to array arguments. The first has to do with variable length arrays, VLAs, a feature of C99 that allows the length of an array to be specified using a non-constant expression. Variable length arrays can also be parameters, as it turns out. Consider the sum underscore array function discussed earlier in this section. Here's the definition of sum underscore array with the body omitted. Int sum underscore array takes in an array A of integers and an int n. As it stands now, there's no direct link between n and the length of the array A. Although the function body treats n as A's length, the actual length of the array could in fact be larger than n, or smaller, in which case the function won't work correctly. Using a variable length array parameter, we can explicitly state that a's length is n. Int SumArray, int n, int a array of n. The value of the first parameter n specifies the length of the second parameter a. Note that the order of the parameters has been switched. Order is important when the variable length array parameters are used. The following version of SumArray is illegal, where we define the array before the length that we're using within the actual array declaration. The compiler will issue an error message at int a index n because it hasn't yet seen n. There are several ways to write the prototype for our new version of sum_array. One possibility is to make it look exactly like the function definition. Int SumArray, int n, int array, size of n, which is version 1. Another possibility is to replace the array length by an asterisk. Int SumArray, int n, int a array, size of asterisk. The reason for using the star notation is that the parameter names are optional in the function declarations. If the name of the first parameter is omitted, it wouldn't be possible to specify the length of the array is n, but the star provides a clue that the length of the array is related to parameters that come earlier in this list. Int SumArray, int bracket star bracket. It's also legal to leave the brackets empty as we normally do when declaring an array parameter. Int SumArray, int n, int array a, which is version 3a, and int SumArray, int array, version 3b. Leaving the brackets empty isn't a good choice because it doesn't expose the relationship between n and a. In general, the length of a variable length array parameter can be any expression. For example, suppose that we were to write a function that concatenates two arrays a and b by copying the elements of a followed by the elements of b into a third array named c. Int concatenate, which takes in int m, int n, an array of size m of integers, an array b of size n of integers, an array c of size m plus n of integers. The length of c is the sum of the lengths of a plus b. The expression used to specify the lengths of c involves two other parameters, but in general it could refer to variables outside the function or even call other functions. Variable length array parameters with a single dimension, as in all our examples so far, have limited usefulness. They make a function declaration or definition more descriptive by stating the desired length of an array argument. However, no additional error checking is performed. It is still possible for an array argument to be too long or too short. It turns out that variable length array parameters are most useful for multidimensional arrays. Earlier in this section, we tried to write a function that sums the elements in a two-dimensional array. Our original function was limited to arrays with a fixed number of columns. If we use a variable length array parameter, we can generalize the function to any number of columns. Int sum two-dimensional array takes in int n, int m, and an array of integers of size n by m. So we have integers I, j, and sum, which is equal to 0. We loop through I up through n and j through m, and we sum equals to the values at array index I, index j. Prototypes for this function include the following. Int sum two-dimensional array, which could be int n, int m, int a, n by m. We could do a asterisk asterisk. We could do just the m, and we could do asterisk just in the column itself. C99, using static in array parameter declarations. C99 allows the use of the keyword static in the declarations of array parameters. The keyword itself existed before C99. Section 18.2 discusses its traditional uses. In the following example, putting static in front of the number 3 indicates that the length of A is guaranteed to be at least 3. int sum array, which takes in an integer array size static 3, and int n. Using static in this way has no effect on the behavior of the program. The presence of static is merely a hint that may allow a C compiler to generate faster instructions for accessing the array. If the compiler knows that an array will always have a certain minimum length, it can arrange to prefetch these elements from memory when the function is called, before the elements are actually needed by statements within the function. One last note about static: if an array parameter has more than one dimension, static can be used only in the first dimension. For example, when specifying the number of rows in a 2D array. Compound literals in C99. Let's return to the original SumArray function one last time. When SumArray is called, the first argument is usually the name of an array, the one whose elements are to be summed. For example, we might call SumArray in the following way, where we have an array B, which has 3, 0, 3, 4, 1 within it. We have total equals to SumArray, which takes in B and 5. The only problem with this argument is that B must be declared as a variable and then initialized prior to the call. If B isn't needed for any other purpose, it can be mildly annoying to create it solely for the purpose of calling SumArray. In C99, we can avoid this annoyance by using a compound literal, an unnamed array that's created on the fly by simply specifying which elements it contains. The following call of SumArray has a compound literal shown in bold as its first argument, where total is equal to SumArray, where we have a casting of int array to this sequence, and then we have the 5. In this example, the compound literal creates an array containing the 5 integers 3, 0, 3, 4, and 1. We didn't specify the length of the array, so it's determined by the number of elements in the literal. We also have the option of specifying a length explicitly within the actual compound literal. Int 4 for the sequence 1921 is equivalent to int 1921. In general, a compound literal consists of a type name within parentheses, followed by a set of values enclosed by braces. A compound literal resembles a cast applied to an initializer. In fact, compound literals and initializers obey the same rules. A compound literal may contain designators, just like a designated initializer, and it may fail to provide full initialization, in which case any uninitialized elements default to 0. For example, the literal int array 10 with a sequence of 8 and 6 has 10 elements. The first two values of 8 and 6, and the remaining have value of 0. Compound literals created inside a function may contain arbitrary expressions, not just constants. For example, we could write expressions for the values within the sequence, where I, j, and k are variables. This aspect of compound literals greatly enhances their usefulness. A compound literal is an L value, so the values of its elements can be changed. If desired, a compound literal can be made read-only by adding the word const to its type, as in const int array with a sequence of 5, 4. Section 9.4, the return statement. A non-void function must use the return statement to specify what value it will return. The return statement has the form return expression, semicolon. The expression is often just a constant or a variable, return 0, return status. More complex expressions are possible. For example, it's not unusual to see the conditional operator used in a return expression. Return if n is greater than or equal to 0, n, else 0. When this statement is executed, the expression n is greater than or equal to 0, return n, else 0 is evaluated first. The statement returns the value of n if it's not negative, otherwise it returns 0. If the type of the expression in a return statement does not match the function's return type, the expression will implicitly convert to the return type. For example, if a function is declared to return an int, but the return statement contains a double expression, the value of the expression is converted to int. Return statements may appear in functions whose return type is void, provided that no expression is given. Return in a void function. Putting an expression in such a return statement will get you a compile time error. In the following example, the return statement causes the function to return immediately when given a negative argument. Void print int I. If I less than 0, return printf I. If I is less than 0, print int will return without calling printf. A return statement may appear at the end of a void function. Void print pun void. Printf to see or not to see, that is the question. Return okay but not needed. Using return is unnecessary though, since the function will return automatically after its last statement has been executed. If a non-void function reaches the end of its body, that is, it fails to execute a return statement, the behavior of the program is undefined if it attempts to use the value returned by the function. Some compilers will issue a warning such as control reaches end of non-void function if they detect the possibility of a non-void function falling off the end of its body. 9.5. Program termination. Since main is a function, it must have a return type. Normally the return type of main is int, which is why the programs we've seen so far have defined main in the following way: int main void, so on and so forth. Older C programs often omit main's return type, taking advantage of the fact that it traditionally defaults to int. Omitting the return type of a function isn't legal in C99, so it's best to avoid this practice. Omitting the word void in main's parameter list remains legal, but as a matter of style, it's best to be explicit about the fact that main has no parameters. We'll see later that main sometimes does have two parameters, usually named argc and argv. The value returned by main is a status code that in some operating systems can be tested when the program terminates. Main should return 0 if the program terminates normally. To indicate abnormal termination, main should return a value other than 0. Actually, there's no rule to prevent us from using the return value for other purposes. It's good practice to make sure that every C program returns a status code even if there's no plans to use it, since someone running the program later may decide to test it. The exit function. Executing a return statement in main is one way to terminate a program. Another is calling the exit function, which belongs to the standard library.h. The argument passed to exit has the same meaning as main's return value. Both indicate the program status at termination. To indicate normal termination, we'd pass 0, exit 0. Since 0 is a bit cryptic, C allows us to pass exit success instead. The effect is the same, exit underscore success. Passing exit underscore failure indicates abnormal termination, exit underscore failure. Exit success and exit failure are macros defined in the standard library.h. The values of exit success and exit value are implementation defined. Typical values are 0 and 1 respectively. As methods of terminating a program, return and exit are closely related. In fact, the statement return expression in main is equivalent to exit expression. The difference between return and exit is that exit causes program termination regardless of which function calls it. The return statement causes the program termination only when it appears in the main function. Some programmers use exit exclusively to make it easier to locate all exit points in a program. 9.6. Recursion. A function is recursive if it calls itself. For example, the following function computes n factorial recursively using the formula n factorial equals to n times n minus 1 factorial. Int fact takes in int n. If n is less than or equal to 1, we're going to return 1, else return n times fact n less than 1. Some programming languages rely heavily on recursion while others don't even allow it. C falls somewhere in the middle. It allows recursion, but most C programmers don't use it that often. To see how recursion works, let's trace the execution of the statement. I equals to fact 3. Here's what happens. Fact 3 finds that 3 is not less than or equal to 1, so it calls fact 2, which finds that 2 is not less than or equal to 1, so it calls fact 1, which finds that 1 is less than or equal to 1, so it returns 1, causing fact 2 to return 2 times 1, which equals to 2, causing fact 3 to return 3 times 2, which equals to 6. Notice how the unfinished calls of fact pile up until fact is finally past 1. At that point, the old calls of fact begin to unwind one by one until the original call, fact 3, finally returns with the answer 6. Here's another example of recursion. A function that computes x to the power of n using the formula x to the power of n equals to x times x to the power of n minus 1. Int power takes in int x and int n. If n is equal to 0, return 1, else return x times power of x and n minus 1. The call power 5,3 would be executed as follows. Power 5,3 finds that 3 is not equal to 0, so it calls power 5,2, which finds that 2 is not equal to 0, so it calls power 5,1, which finds that 1 is not equal to 0, so it calls power 5,0, which finds that 0 is equal to 0, so it returns 1, causing power 5,1 to return 5 times 1, which equals to 5, causing power 5,2 to return 5 times 5, which equals to 25, causing power 5,3 to return 5 times 25, which is 125. Incidentally, we can condense the power function a bit by putting a conditional expression in the return statement. Return if n is equal to 0, 1, else x times power of x n minus 1. Both fact and power are careful to test a termination condition as soon as they're called. When fact is called, it immediately checks whether its parameter is less than or equal to 1. When power is called, it first checks whether its second parameter is equal to 0. All recursive functions need some kind of termination condition in order to prevent infinite recursion. The quick sort algorithm. At this point, you may wonder why you're bothering with recursion. After all, neither fact nor power really needs it. Well, you've got a point. Neither function makes much of a case for recursion because each calls itself just once. Recursion is much more helpful for sophisticated algorithms that require a function to call itself 2 or more times. In practice, recursion often arises naturally as a result of an algorithm design technique known as divide and conquer, in which a large problem is divided into smaller pieces that are tackled by the same algorithm. A classic example of the divide and conquer strategy can be found in the popular sorting algorithm known as quicksort. The quicksort algorithm goes as follows. For simplicity, we'll assume that the array being sorted is indexed from 1 to n. 1. Choose an array element E, the partitioning element. Then, rearrange the array so that elements 1 through I less than 1 are less than or equal to E. Element I contains E, and elements I plus 1 up to n are greater than or equal to E. Sort elements 1 through I less than 1 by using quicksort recursively. Sort elements I plus 1 through n by using quicksort recursively. After step 1, the element E is in its proper location. Since the elements to the left of E are all less than or equal to it, they'll be in their proper places. Once they've been sorted, in step 2, the similar reasoning applies to the elements to the right of E. Step 1 of the quicksort algorithm is obviously critical. There are various methods to partitioning an array, some much better than others. We'll use a technique that's easy to understand but not particularly efficient. I'll first describe the partitioning algorithm informally. Later, we'll translate it into C code. The algorithm relies on two markers named low and high, which keep track of positions within the array. Initially, low points to the first element of the array, and high points to the last element. We start by copying the first element. the partitioning element into a temporary location elsewhere, leaving a quote-unquote hole in the array. Next, we move high across the array from right to left until it points to an element that's smaller than the partitioning element. We then copy the element into the hole that low points to, which creates a new hole pointed to by high. Now we move low from left to right, looking for an element that's larger than the partitioning element. When we find one, we copy it into the hole that high points to. This process repeats with low and high taking turns until they meet somewhere in the middle of the array. At that time, both will point to a hole. All we need to do is copy the partitioning element into the hole. The following diagrams illustrates how quicksort would sort an array of integers. Let's start with an array containing 7 elements. Low points to the first element, high points to the last one. So our low, which is our low index, points to the first, and our high points to the last. Note that low is not pointing to the highest value here in the array, or second highest, right, or third highest, whatever. It's just the low index. The first element, 12, is the partitioning element. Copying it somewhere else leaves a hole at the beginning of the array. Now, we compare the element pointed to by high with 12. Since 10 is smaller than 12, it's on the wrong side of the array, so we move it to the hole and shift low to the right. Low points to the number 3, which is less than 12, and therefore doesn't need to be moved. We shift low to the right instead. And since 6 is also less than 12, we shift low again. Low now points to 18, which is larger than 12, and therefore out of position. After moving 18 to the hole, we shift high to the left. High points to 15, which is greater than 12, and thus doesn't need to be moved. We shift high to the left and continue. So our high now points at 7. High points to 7, which is out of position. After moving 7 to the hole, we shift low to the right. Low and high are now equal, so we move the partitioning element to the hole. At this point, we've accomplished our objective. All elements to the left of the partitioning element are less than or equal to 12, and all elements to the right are greater than or equal to 12. Now that the array has been partitioned, we can use quicksort recursively to sort the first 4 elements of the array, 10, 3, 6, and 7, and the last 2, 15, and 18. Program, quicksort. Let's develop a recursive function named quicksort that uses the quicksort algorithm to sort an array of integers. To test the function, we'll have main read 10 numbers into the array, call quicksort to sort the array, then print the numbers in the array. Enter 10 numbers to be sorted. 10 numbers are entered. In sorted order is the sorted order of numbers. Since the code for partitioning the array is a bit lengthy, we'll put in some separate functions named split. Okay, quicksort sorts an array of integers using quicksort algorithm. We include the standard io.h and we define n to be 10. We have a quicksort function which returns a void type, has an array element of integers, int low and int high. We have a function int split, which takes in an array of integers, a low int and a high int. And then we have our main function, where we define array A to be a size n, and we define integer I. Printf is equal to enter %d numbers to be sorted, and we put in the macro n. For I equals to 0, while I is less than n, I++, scanf the numbers that the user enters into the array A at index of I. We're then going to call quicksort on the array with 0 being our low and n-1 being our high, and printing the values. We then have our quicksort function, which takes in the array a low and a high. We declare int middle. We say if low is greater than or equal to high, we return, meaning that our low either became at equal to high or crossed over. and middle is equal to split the array A and low and high. Then we call quicksort on the left half and call quicksort on the right half recursively. So our split function is here. We take in the array low and high. We have our partitioning element, which is the array index of low. Right? We infinitely loop here. While low is less than high, and the partitioning element is less than or equal to the array at index of high, we continually decrease high. If low is greater than or equal to high, we'll break. And then the array at index of low plus plus is equal to array at index of high. So this increases our low in line here after this is called. Right? So we'll use our current value of low, and then after this line, it'll increase. While low is less than high, and the array at index of low is less than or equal to partitioning element, we're going to continually increase the low, so the inverse of this above statement for the partitioning element relation to the high versus low. If the low is greater than or equal to the high, we will break, and at array index of high minus minus, which equals to array index of low. Once this loop breaks, we will set array at index of high equals to the partitioning element and return high. Although this version of quicksort works, it's not the best. There are a number of ways to improve the program's performance, including improving the partitioning algorithm. Our method isn't the most efficient. Instead of choosing the first element in the array as a partitioning element, it's better to take the median of the first element and the middle element and the last element. The partitioning process itself can also be sped up. In particular, it's possible to avoid the low less than high tests in the two while loops. Using a different method to sort small arrays. Instead of using quicksort recursively all the way down to arrays with one element, it's better to use a simpler method for small arrays, those with fewer than, say, 25 elements. Making quicksort non-recursive. Although quicksort is a recursive algorithm by nature, and it's easiest to understand in recursive form, it's actually more efficient if the recursive is removed. For details about improving quicksort, consult a book on algorithm design such as Algorithms in C, Parts 1 through 4, Fundamentals, Data Structures, Sorting, and Searching. Q&A. Some C books appear to use terms other than parameter and argument. Is there any standard terminology? As with many other aspects of C, there's no general agreement on terminology, although the C89 and C99 standards use parameter and argument. The following table should help you translate. This book, parameter argument. Other books, formal argument, formal parameter, actual argument, actual parameter. Keep in mind that when no confusion would result, I sometimes deliberately blurred the distinction between the two terms using argument to mean either. Question. I've seen programs in which parameter types are specified in separate declarations after the parameter list, as in the following example. Double average AB, double AB, return A plus B over 2. Is this practice legal? This method of defining functions comes from KNRC, so you may encounter it in older books and programs. C89, C99 support this style so that older programs will still compile. I'd avoid using it in newer programs, however, for a couple of reasons. First, functions that are defined in older ways aren't subject to the same degree of error checking. When a function is defined in the older way and no prototype is present, the compiler won't check that the function is called with the right number of arguments, nor will it check that the arguments have the proper types. Instead, it will perform the default argument promotions. Second, the C standard says that the older style is obsolescent, meaning that its use is discouraged and it may be dropped from C eventually. Question. Some programming languages allow procedures and functions to be nested within each other. Does C allow function definitions to be nested? No, C does not permit the definition of one function to appear in the body of another. Among other things, this restriction simplifies the compiler. Question. Why does the compiler allow the use of function names that aren't followed by parentheses? We'll see in later chapters that the compiler treats a function name not followed by parentheses as a pointer to the function. Pointers to function have legitimate uses, so the compiler can't automatically assume that a function name without parentheses is an error. The statement print pun without a parentheses is legal because the compiler treats print pun as a pointer and therefore an expression, making this a valid, although pointless expression statement. Question. In the function call F, A, and B, how does the compiler know whether the comma is punctuation or whether it's an operator? It turns out that the arguments in a function call can't be arbitrary expressions. Instead, they must be assignment expressions, which can't contain commas used as operators unless they're enclosed in parentheses. In other words, in the call f a comma b, the comma is punctuation. In the call f parentheses parentheses a comma b parentheses parentheses, it's an operator. Do the names of the parameters in a function prototype have to match the names given later in the function definition? No, some programmers take advantage of this fact by giving long names to parameters in the prototype, then using shorter names in the actual definition. Or French-speaking programmers might use English prototypes, then switch to more familiar French names in function definitions. I still don't understand why we bother with function prototypes if we just put definitions of all the functions before main. We're covered, right? Wrong. First, you're assuming that only main calls the other functions, which is unrealistic. In practice, some of the functions will call each other. If we put all the function definitions above main, we'll have to watch their order carefully. Calling a function that hasn't been defined yet can lead to big problems. But that's not all. Suppose that two function calls each other, which isn't as far-fetched as it may sound. No matter which function we define first, it will end up calling a function that hasn't yet been defined. But there's still more. Once programs reach a certain size, it won't be feasible to put all the functions in one file anymore. When we reach that point, we'll need to prototypes to tell the compiler about functions in other files. Question: I've seen function declarations that omit all information about parameters. Double, average. Is this legal? Yes, this declaration informs the compiler that average returns a double value, but provides no information about the number and types of its parameters. Leaving the parentheses empty doesn't necessarily mean the average has no parameters. In K and RC, this form of function declaration is the only one allowed. The form that we've been using, the function prototype in which the parameter information is included, was introduced in C89. The older kind of function declaration is now obsolescent, although we still allow it. Why would a programmer deliberately omit parameter names in a function prototype? Isn't it easier to just leave the names? Omitting parameter names in prototypes is typically done for defensive purposes. If a macro happens to have the same name as a parameter, the parameter name will be replaced during preprocessing, thereby damaging the prototype in which it appears. This isn't likely to be a problem in small programs written by one person, but can occur in large applications written by many people. Question: is it legal to put a function declaration inside the body of a function? Yes, here's an example. Int main void double average double A double B. This declaration of average is valid only for the body of main. If other functions need to call average, they'll each have to declare it. The advantage of this practice is that it's clear to the reader which functions call which other functions. In this example, we see that the main function will be calling average. On the other hand, it can be a nuisance if several functions need to call the same function. Even worse, trying to add and remove declarations during program maintenance can be a real pain. For these reasons, I'll always put function declarations outside function bodies. If several functions have the same return type, can their declarations be combined? For example, since both printPun and printCount have void as the return type, is the following declaration legal? Void printPun void, comma printCount int n. Yes, in fact, C even allows us to combine function declarations with variable declarations. Combining declarations in this way isn't usually a good idea, though it can be easily confused. What happens if I specify a length for a one-dimensional array parameter? The compiler ignores it. Consider the following example. Double inner product, double with array of size 3, double array W size 3. Other than documenting that inner product's arguments are supposed to be arrays of length 3, specifying a length doesn't buy us much. The compiler won't check that the arguments actually have length 3. There's no added security. In fact, the practice is misleading in the fact that it suggests that inner product can only be passed arrays of length 3, when in fact it can be passed arrays of any arbitrary length. Why can the first dimension of an array parameter be left unspecified but not the other dimensions? First, we need to discuss how arrays are passed in C. As section 12.3 explains, when an array is passed to a function, the function is given a pointer to the first element in the array. Next, we need to know how the subscripting operators work. Suppose that A is a one-dimensional array passed to a function. When we write A index of I is equal to 0, the compiler generates instructions that compute the address of A index of I by multiplying I by the size of an array element and adding that result to the address that A represents. The pointer passed to the function. This calculation doesn't depend on the length of A, which explains why we can omit it when defining the function. What about multi-dimensional arrays? Recall that C stores arrays in row major order, with the elements in row 0 stored first and the elements in row 1, and so forth. Suppose that array A is a two-dimensional array point parameter, and we write array A index I index j equal to 0. The compiler generates instructions to do the following. 1. Multiply I by the size of a single row A. 2. Add this result to the address that A represents. 3. Multiply j by the size of an array element. And 4. Add this result to the address computed in step 2. To generate these instructions, the compiler must know the size of a row in the array, which is determined by the number of columns. The bottom line, the programmer must declare the number of columns in A. That's why when we're declaring arrays, we could omit the rows, but we could give columns. We have to declare columns. Why do some programmers put parentheses around the expression in a return statement? The examples in the first edition of Kernighan and Ritchie's The C Programming Language have parentheses and return statements, even though they aren't required. Programmers and authors of subsequent books picked up the habit from K&R. I don't use these parentheses since they're unnecessary and contribute nothing to readability. K&R apparently agree. The return statement in the second edition of the C Programming Language lack parentheses. What happens if a non-void function attempts to execute a return statement that has no expression? That depends on the version of C. In C89, executing a return statement without an expression in a non-void function causes undefined behavior, but only if the program attempts to use the value returned by the function. In C99, such a statement is illegal and should be detected as an error by the compiler. How can I test main's return value to see if a program has terminated normally? That depends on your operating system. Many operating systems allow this value to be tested within a batch file or a shell script that contains commands to run several programs. For example, the line if error level 1 command. In a Windows batch file will execute command if the last program terminated with a status code greater than or equal to 1. In Unix, each shell has its own method for testing the status code. In the Bourne shell, the variable $? Contains the status of the program run. The C shell has a similar variable, but its name is $status. Question: why does my compiler produce a control reaches end of non-void function warning when it compiles main? The compiler has noticed that main, despite having int, has its return type, doesn't have a return statement. Putting the statement return 0 at the end of the main will keep the compiler happy. Incidentally, this is good practice even if your compiler doesn't object to the lack of a return statement. When a program is compiled using C99 compiler, this warning shouldn't occur, and C99 is okay to fall off the end of a main without returning a value. The standard states that main automatically returns 0 in this situation. Question: with regard to the previous question, why not just define main's return type to be void? Although this practice is fairly common, it's illegal according to C89 standard. Even if it weren't illegal, it wouldn't be a good idea, since it presumes that no one ever will test the program's status upon termination. C99 opens the door for legalizing this practice by allowing the main to be declared, quote, in some other implementation-defined manner, close quote, with a return type other than int or parameters other than those specified by the standard. However, any usage isn't portable, so it's best to declare main's return type to be int. Question: is it legal for a function f1 to call f2, which then calls f1? Yes. This is just an indirect form of recursion in which one call of f1 leads to another, but make sure that either f1 or f2 eventually terminates. And boom. Awesome. All right, you guys, that was Chapter 9, Functions, in C Programming, a Modern Approach, second edition by K.N. King, which covers both C89 and C99. We've been teaching ourselves C programming from scratch here live on the channel. If you guys enjoyed this read-along of the stream, please like and subscribe. The notes that you see on the right side of my screen can be found within my GitHub in the description. This has been the condensed version of the live stream. If you guys would like to see the full unedited version of me reading this chapter and solving the problems, consider jumping on the live stream where I teach myself how to code in both C and Python almost every single day. All right, you guys, this was chapter 9, wrapped up in C Programming, a Modern Approach, second edition by Ken King. Thanks so much for being here, and I'll see you guys in the next one. Peace.